Welcome everyone to page number 8 from the fall semester 2014 final exam for Math 234. In this problem, let's see, find the work done by the vector field over the path r of t, which is equal to cosine of t I, sine of t j, and just t k's, as t ranges from 0 to pi over 2. So okay, we need to remember work done by a vector field, right, is kind of this code phrase, more or less, right, which says we need to integrate over this curve f dot t ds. All right, there were lots of different ways to represent this, so this was one of them. Oops, sorry, f dot t small s here. Another way to do this, right, was the integral over curve of f dot dr, right? There were lots of ways to represent this stuff, right? So this is the work done by a vector field. So this is saying evaluate the line integral over this vector field, right? This is one of these code phrases that means, okay, take the line integral. Okay, so we need to decide, right? We know lots of different ways to evaluate out line integrals. So let's kind of go through the checklist really quick. This will be a nice review. So if I wanted to think about using Green's theorem, right? So first of all, we should quickly rule out Green's theorem because this is in 3 dimensions, right? So I have an I, a j, a k, and our vector field, right? And our curve, right, is parameterized with i's, j's, and k's. So we can't use Green's theorem. But there were upgrades of Green's theorem, right? So for instance, if I wanted to use maybe Stokes' theorem has a way that we can transform a line integral like this. But unfortunately, right, this curve right here is not closed, so it can't be the boundary of any surface. And so we have to rule out Stokes' theorem as well. Okay, so we can't use Green's theorem, we can't use Stokes' theorem. How about the fundamental theorem of line integrals, right? The fundamental theorem of line integrals, that's actually had, right, when you have curves that aren't closed, so maybe something like this, you know, in space. So we could use maybe the fundamental theorem of line integrals. Can we use that? Well, if you've tried this, or if you pause the video and you try it, right, in order to use the fundamental theorem of line integrals, we need a conservative vector field, right? We need to be able to find a potential function. And so if you just ask yourself, is this vector field right here conservative? Well, then you'll calculate out the curl and see if the curl is equal to the vector 0. But unfortunately, the curl is not 0 in this case. So that rules out the fundamental theorem of line integrals. So after all that, right, kind of the last thing that maybe you think about is, well, we know how to just evaluate this the regular way, right, that we actually learned in 16.2. And so that's what we need to do in this case. So let's go ahead and evaluate out this line integral just using our regular technique back from 16.2. So it's nice to us. It's already given us the parameterization. So let's go ahead and set this up. So I'm going to have, let's see, y, negative x, and z squared. And we're going to dot with dr, right? So I'm going to take the derivative of this here. So the derivative of cosine is going to be negative sine. The derivative of sine is going to be cosine. The derivative of t is going to be 1 dt. And of course, we're integrating from 0 to pi over 2. Now, of course, this is a bit disturbing, right? Because we have y's and x's and z's, and I want to integrate with respect to t. So I need to get all t's. So remember, this is our x coordinate, or this is our y coordinate, this is our z coordinate, right? So everywhere I see an x, I'm going to plug in cosine. Everywhere I see a y, I'm going to plug sine. Everywhere I see a z, I'm going to plug in t. And then we're going to have this all in terms of t's. So let's see, we have sine, negative cosine, and let's see, z squared, aka t squared. And we're going to be dot producting that with negative sine t, cosine t, 1. So we go ahead and we do the dot product. I get, let's see, negative sine squared t minus cosine squared t plus t squared dt. We're evaluating this. We're going to integrate from 0 to pi over 2. All right, so we see here, if I was to factor out a negative, right, I would have sine squared plus cosine squared. So therefore, this is just going to be negative 1. So we can do a little bit of simplification. So that's very nice. And now we can go ahead and integrate this. Let me go ahead and take away these parentheses. So let's see, when I integrate this, I'm going to get negative t plus 1/3 t cubed. And we're going to evaluate that from 0 to pi over 2. So in this case, when you plug in 0, of course, you get out 0. If you plugged in pi over 2, let's see, we'd get negative pi over 2, and then plus 1/3 pi over 2 cubed. And you can go ahead and leave your final answer like this if you'd like, or you can go ahead and simplify out that cube and whatnot And let's see, we would get negative pi over 2. And let's see, in the numerator we would have pi cubed. And let's see, in the denominator we would have 3 times 8. So 3 times 8 would be 24. So either one of these, 100%. All right, so there's evaluating out a line integral. Let's go ahead and move on to the last problem for this page. Use Green's theorem to evaluate out the line integral. In fact, this is probably telling us too much here. I would like us to imagine, really quick, that you just see this, right? Evaluate out the line integral where f, right, we have this nice given vector field here, and c is the positively oriented triangle shown below. So, okay, I want you guys to be able to realize when you can and can't use Green's theorem, right? So in this case, the claim is, right, if we go down this list, trying to evaluate out this line integral, right, f dot dr. So, and we have to think about, okay, what are the different ways that we can do this? And we say, well, what about Green's theorem, right? That's kind of where I started last time anyway. And so, yes, we have only 2 components, right? An x component and a y component or so. So there's only 2 components for our vector field, and we're in the xy plane. Those are all good signs, right? And we have a closed curve, right? It goes all the way around. It's the boundary for some region here, right? Moreover, I mean, it even says here that it's positively oriented, right? It goes in this counterclockwise direction. So yes, this is well set up for Green's theorem. So even if it didn't say use Green's theorem, we should still be able to identify, for something like this, I'm going to use Green's theorem. So according to Green's theorem, we can go ahead and trade in this line integral for the double integral over the region. So let's go ahead and maybe shade in and be very explicit. Where is our region? So the curve is the boundary of this region. And then the inside here, right, this is going to be the D. Right, this is the 2-dimensional region that we're going to be integrating over. And we need q sub x minus p sub y dA. All right, so q sub x, right, here's my p and here's my q. So if I take the derivative of q with respect to x, well, luckily, right, this all has just y's in it, so that's going to be 0. And so the derivative of q with respect to x is just going to be negative 4. Subtract away p sub y. So if I look at p sub y, well, I'm going to have 6. And then this bit right here only has x's in it. So this is going to be 6 plus 0, aka just 6. All right, this is very, very nice. It looks like we have a negative 10. I'm going to go ahead and factor that out. And now this is just going to be integrating 1 over this region. So when I'm integrating 1 over this region, well, that's just going to be the area formula for a triangle, right? Because this is the same thing as area. So I'm going to have negative 10 times 1/2 the base. So my base down here, it looks like it has length 2, times the height. So the height here also 2. So 1/2 base times height, there's a little bit of cancellation, and I'm going to get the answer negative 20. So all things considered, I think this is a pretty nice application of Green's theorem. All right, that's my final answer, and that's it for this video. See you guys next time.